Let's dive right into one of the most counterintuitive and difficultly simple branch of mathematics, combinatorics. Simple arrangements. We'll start our shallow wade into combinatorics with a simple problem. Suppose a person wishes to arrange 3 books on a shelf. All books are distinguishable from one another, and the person does not mind which books end up where. How many possible arrangements are there? Let's name the 3 books A, B, and C. The possible combinations are ABC, ACB, BAC, BCA, CAB, and CBA. In short, there are 6 different arrangements that are possible. How about if a person wishes to arrange 4 books on a shelf? Since the number is still relatively small, we can list out the possible arrangements with the 4 books A, B, C, and D. The possible combinations are ABCD, ABDC, ACBD, ACDB, ADBC, ADCB, BACD, BADC, BCAD, BCDA, going all the way to DCBA. There are 24 different arrangements that are possible for 4 books. As you can see, the number of books to be arranged increases, so does the number of possible arrangements. Pretty soon it becomes incredibly tedious to list down all of the possible arrangements. Fortunately, there is a trick at hand. Imagine that we want to arrange 5 different books on a shelf, and we represent the 5 possible spaces with horizontal lines. There are 5 possible books A, B, C, D, E, and E. In the first space, there are 5 possible books that can be placed there. In the second space, though, there are only 4 possible books that can be placed there, since one was already placed in the previous space. In the third space, there are 3 possible books that can be placed there, and so on until the last space, in which there is only 1 possibility. The total number of arrangements for placing 5 books on the shelf is 5 times 4 times 3 times 2 times 1, or 120. A similar operation can be conducted with 6 different books. 6 times 5 times 4 times 3 times 2 times 1, or 720, or 7 or 8, or any reasonable number. This operation is known as the factorial, and is written in the form n factorial. In general, n factorial is equal to n times n minus 1 times n minus 2 times all the way up to 1 for all positive integers n. 0 factorial is defined as 1. Summarizing, the number of possible arrangements of n distinct objects is n factorial. Special arrangements. Let's take a look at some cases that deviate from the fairly straightforward arrangements that we have presented before. Suppose that the same person wishes to arrange 7 different books on a shelf. The books come in 3 types: 3 science, 2 maths, and 2 novels. What is the total number of arrangements possible? That is simply 7 factorial, or 5,040 possible arrangements. But now suppose that the person wishes to keep the 3 science books together. How many possible arrangements are there now? To solve this case, suppose that the 3 science books are 1 object, so we only have to arrange 5 objects for a total of 5 factorial 120 cases. However, there are 3 factorial, or 6 different arrangements of the 3 science books possible, giving rise to a total of 5 factorial times 3 factorial, or 720 cases. Instead, what happens if the person wishes to keep the 3 science books separated? To find that answer, we merely have to subtract the number of arrangements with the 3 science books kept together from the total number of arrangements. In other words, we must subtract 6 factorial from 7 factorial, which is 4,320 possible arrangements. Permutations and combinations. There are 2 large categories of arrangement in combinatorics: permutations and combinations. Permutations are arrangements in which the order matters, and combinations are arrangements in which the order does not matter. All of the previous examples of arrangements were permutations in which the order of arrangements mattered. This was because every single object to be arranged was distinguishable from one another, and hence, arranging the books ABC was different from CAB. Let's solve a standard permutation question. There are 9 candidates to receive 3 medals, gold, silver, and bronze, and one student can receive 1 medal at most. How many possible arrangements are there? Firstly, identify that the problem is one pertaining to permutation, since the 3 medals are distinguishable from one another. We model the 3 medals as horizontal lines again. Note that the first one is gold, the second silver, and the third bronze. There are 8 possible choices for the gold medal. However, there are only 7 possible choices for the silver medal, and subsequently 6 possible choices for the bronze medal. In total, there are 8 times 7 times 6, or 336 choices. But how do we generalize this formula? The equation seems to be a variant of 8 factorial, except without 5 factorial. In short, the total number of possible permutations is 8 factorial over 5 factorial. Let's imagine that there are 10 possible candidates with 4 possible metals, gold, silver, bronze, and steel. How many permutations are possible? This time, the answer is 10 times 9 times 8 times 7, or 5040. Represented, it's 10 factorial over 6 factorial. We have reached a curious pattern where the total number of permutations depend on the total number of students and the difference between the number of students and the number of medals. Or, generalizing this, the permutation of R objects selecting from a set of N objects is represented by NPR, which is N factorial over N minus R factorial. Combinations are simpler than permutations, as there are fewer combinations than permutations. Suppose that 2 students are to be chosen randomly from a group of 5 students. How many possible pairs are possible? For now, assume that every pair is unique. AB is different from BA. This problem then becomes a permutation that can be represented by 5p2, or 20 possible permutations. However, the pairs are not all distinct, as AB is identical to BA. Since there are 2 students per pair, we have repeated every possible combination twice. Therefore, the total number of combinations is not 20, but 10. The general formula for the number of combinations of R items chosen from a group of N items is NCR, which is N factorial over R factorial times N minus R factorial. In a sense, NCR is NPR over R factorial, where R factorial eliminates the repetitions of each grouping. Pascal's triangle, one of the most famous mathematical structures, is also related to combinatorics. Every term in the triangle corresponds to a combination NCR, where n is the row number and r is the order number from left to right, starting from 0. Thus, rows 0 to 4 of the Pascal's triangle can be represented like this. Combinations with repetition. Sometimes combinations are a bit more complex than the simple NCR. Let's solve a few problems together. A person needs to buy 10 flowers, which come in 2 types, roses and lilies. There needs to be at least 1 rose and at least 1 lily. How many possible combinations are there? Since 1 rose and 1 lily is guaranteed, we only have to work with 8 flowers. This will be represented with 8 circles. We can draw 9 horizontal lines in between, in front of, and behind the 8 circles. Because we are dealing with 2 types of object, we can differentiate the objects by using 1 partition, represented by a vertical line. There are 9 different locations the partition can be placed at, giving rise to a total of 9 combinations. Fair enough. Let's try a slightly more difficult problem. There are 24 apples that need to be distributed to 3 people each. Each person is to receive at least 2 apples. How many possible combinations are there? Like the previous example, we begin by reducing the number of items to 18 apples. The 18 apples are represented by 18 circles. Unfortunately, this time there are 2 partitions, since the apples have to be distributed to 3 people, which cannot be easily counted. However, there is a solution at hand. By pretending that the 18 circles and the 2 partitions are all distinct, we can find the total number of permutations of these 20 items, which is 20 factorial. However, since we have repeated identical arrangements, we have to divide 20 factorial by the factorial of the number of apples and the number of partitions, giving way to 20 factorial over 18 factorial times 2 factorial, or 190 combinations. Conclusion. Combinatorics is a challenging subject of mathematics that students will face throughout their journey from middle school to university. Yet, with an accurate understanding of the meaning of the formulae and the methods used to derive them, combinatorics can be resolved in the end.